German U-boats ruled the Atlantic until Huff-Duff radios started hunting them. Opening sequence. The year is 1942. The North Atlantic is a graveyard. Every day, somewhere in those dark waters, Allied merchant ships are dying. Their hulls torn open by torpedoes, their crews swallowed by frigid seas that give them perhaps 15 minutes to live. The lifeboats, when they launch successfully, drift for days or weeks. Most men never make a home. This isn't warfare as soldiers understand it on land. There are no front lines here, no trenches to defend, no territory to capture and hold. Instead, there's an immense emptiness punctuated by sudden, catastrophic violence. A convoy of 40 ships steams eastward, carrying the fuel, food, and ammunition that Britain desperately needs to survive. Then, without warning, a column of water erupts alongside a tanker. The explosion echoes across the water. The ship begins listing immediately. Within minutes, burning oil spreads across the surface. The attacker remains invisible. Somewhere beneath the waves, a German U-boat commander peers through his periscope, already lining up his next shot. His submarine carries enough torpedoes for several more kills. The convoy's escort ships race around frantically, dropping depth charges that send up white plumes but rarely find their target. By dawn, 3 more ships have gone down. The U-boat has slipped away, diving deep, running silent, impossible to track. This was the Battle of the Atlantic, and for the first 3 years of World War II, Germany was winning it decisively. British Prime Minister Winston Churchill would later write that the U-boat peril was the only thing that truly frightened him during the war. The mathematics were brutal and simple. Britain imported nearly all its fuel and half its food. If the supply lines across the Atlantic were severed, the island would starve and the war effort would collapse. No amount of courage or determination could overcome empty fuel tanks and empty stomachs. The German submarine force, the Unterseebetwaffe, had turned the Atlantic into a killing field. At their peak effectiveness, U-boats were sinking Allied shipping faster than new vessels could be built. The losses were staggering. Hundreds of ships, hundreds of thousands of tons of cargo, tens of thousands of lives. And the submarines seemed nearly unstoppable. They could strike from any direction, at any time, then vanish into the depths before retaliation arrived. But warfare is a contest of innovation and adaptation. While U-boats dominated through 1942, the Allies were developing a range of technologies to counter the threat. Some were obvious, like better sonar and more escort ships. Others were complex, like improved radar systems and aerial patrol aircraft. But one technology, initially dismissed as a minor tool, would prove absolutely decisive in turning the tide of the battle. That technology was high-frequency direction finding, universally known by its abbreviated nickname, Huff-Duff. And while it sounds almost comical, this radio detection system would ultimately break the back of the U-boat campaign and help ensure Allied victory in World War II. This is the story of how electronic warfare came of age in the crucible of the Atlantic, how physicists and engineers became as important as sailors and submariners, and how invisible radio waves proved more lethal than torpedoes. It's the story of how the hunters became the hunted. Hashtag the U-boat threat. Dominance beneath the waves. To understand why Huff-Duff mattered so profoundly, we must first understand the problem it solved. The German U-boat force represented a nearly perfect weapon system for disrupting maritime commerce. And by 1942, they had refined their tactics to devastating effect. The Type 7 U-boat, the workhorse of the German submarine fleet, was an engineering marvel of its time. At roughly 67 meters long and displacing about 770 tons when surfaced, these vessels carried a crew of 44 men crammed into spaces that would make a sardine can look spacious. But within that tight envelope, German engineers had packed remarkable capability. A Type 7 could travel over 8,500 nautical miles at economical speed, remaining at sea for extended patrols. It carried 14 torpedoes, devastating weapons that could break the keel of a large merchant ship with a single hit. Crucially, the U-boat could make 17 knots on the surface using its diesel engines, faster than most merchant convoys could steam. This speed advantage was absolutely critical to German tactics. The key to understanding U-boat effectiveness lies in recognizing that these weren't really submarines in the modern sense. Rather, they were submersible torpedo boats. They spent most of their operational time on the surface, where they could run their diesel engines, charge their batteries, travel quickly, and maintain good visibility for hunting. They submerged primarily to attack, to evade counterattacks, or to hide during daylight hours when aircraft might spot them. When submerged, a U-boat's capabilities degraded dramatically. Running on battery power alone, it could manage only about 7 to 8 knots for short periods before exhausting its batteries, and only 4 knots for extended underwater running. The crew breathed stale air that grew increasingly foul and oxygen depleted. Every system was powered down to conserve energy. A U-boat could remain submerged for perhaps 24 hours at most, and that was in emergency situations. Far more commonly, they would dive for a few hours at most. This operational reality shaped everything about U-boat tactics. Admiral Karl Donitz, the commander of the German submarine force, had developed a tactical doctrine that maximized the U-boat's surface capabilities while minimizing exposure to its underwater vulnerabilities. This doctrine was called Rudel-Taktik, the wolf pack tactic. Here's how it worked. Rather than patrolling individually, U-boats would be positioned in long lines across likely convoy routes, creating a picket line that might stretch hundreds of miles. When one U-boat spotted a convoy, usually this happened at night or in poor weather when the submarine's low profile made it nearly invisible, that boat would not immediately attack. Instead, it would shadow the convoy and transmit radio reports to U-boat headquarters in France. These radio messages were the key to the entire system. The shadowing U-boat would send regular position reports, allowing headquarters to vector other submarines toward the convoy. Over several hours, or even a day, more U-boats would arrive, gathering like wolves around a herd. Only when sufficient forces had assembled would the attack begin. And when it came, the attack was terrifying. The U-boats would strike at night, on the surface, when darkness rendered them nearly invisible. The submarines would race in at high speed, slip between the columns of merchant ships, and fire their torpedoes at point-blank range, sometimes as close as 500 meters. At such distances, it was almost impossible to miss. A skilled commander could fire a spread of torpedoes and expect multiple hits. The chaos was extraordinary. Merchant ships would suddenly erupt in flame. Some broke in half and sank within minutes. Others drifted, crippled and burning, their crews scrambling to launch lifeboats in the darkness. The convoy would scatter, ships fleeing in all directions or attempting to maintain formation while dodging around sinking vessels. Escort ships would race back and forth, firing star shells to illuminate the scene and desperately trying to locate the attackers. But finding a surfaced U-boat at night was extraordinarily difficult. The submarine presented a low silhouette, perhaps only a few meters of conning tower visible above the water. They were painted in dark colors that absorbed light, and they were fast, faster than most escort corvettes could manage. If pursued, a U-boat could simply run away on the surface, opening the distance until it was safe to crash dive and slip away underwater. The British Royal Navy's escort forces were stretched desperately thin. In 1941 and early 1942, a typical convoy might have only 3 or 4 escort vessels to protect 30 or 40 merchant ships. The escorts carried depth charges for attacking submerged submarines, but these were largely useless against surface-running U-boats. Their sonar, called ASTIC by the British, could detect submerged submarines reasonably well, but it was worthless against surface targets and effective range was limited to about 1,500 meters at best. Meanwhile, the submarines could attack again and again. A wolf pack of 8 or 10 U-boats might spend several nights attacking the same convoy, working methodically through the merchant ships, diving briefly when pressed by escorts, then resurfacing to continue the slaughter once the escorts had moved away. Some convoys lost a dozen ships or more in these running battles. The statistics tell the story. In 1940, U-boats sank over 2.1 million tons of Allied shipping. In 1941, the figure climbed to 2.3 million tons. In 1942, it exploded to 6.2 million tons, an average of more than 500,000 tons per month. At that rate, the Allies were losing ships faster than their shipyards could replace them, despite a massive construction program. Individual convoys suffered catastrophically. Convoy SC, 7 in October 1940, lost 20 of its 35 ships. Convoy HX, 229/SC, 122 in March 1943, lost 21 ships in a single battle. These weren't just cargo statistics. Each ship represented lives, often dozens of crew members per vessel, and precious cargo that Britain desperately needed. The U-boat crews called this period Die glückliche Zeit, the happy time. From a perspective, the hunting was easy and the targets plentiful. A successful U-boat might sink 50,000 tons of shipping in a single patrol. Commanders became aces, celebrated in German propaganda. The U-boat force was Germany's elite service, attracting the best recruits, receiving priority for resources and technology. But the happy time rested on a vulnerability that the Germans didn't initially recognize. The wolf pack tactic, so devastatingly effective, required constant radio communication. U-boats had to transmit position reports when they sighted convoys. Headquarters had to broadcast orders directing other submarines toward the target. The shadowing boat had to send regular updates on the convoy's course and speed. These transmissions were encrypted using the famous Enigma cipher machine, which the Germans believed was unbreakable. And indeed, breaking Enigma was extraordinarily difficult. It required the combined efforts of brilliant mathematicians at Bletchley Park and captured code materials from U-boats and other vessels. Even when the Allies could decrypt messages, the intelligence had to be acted upon carefully to avoid revealing that the code had been broken. But there was another way to use those radio transmissions, one that didn't require breaking the code at all. You didn't need to read the message to know where it came from. Radio waves travel in straight lines, and their direction of arrival can be measured. This was the fundamental principle behind direction finding, and it had been used for decades. Ships carried direction-finding equipment that could take bearings on radio transmissions, getting a rough idea of where the signal originated. The problem was that traditional direction-finding equipment was large, inaccurate, and slow. It took several minutes to get a bearing, and that bearing might be off by 10 or 20 degrees. 2 or more stations, widely separated, could cross their bearings to triangulate a transmitter's position, but this required coordination and time. By the time the calculations were complete, a mobile transmitter, like a U-boat, might have moved miles from its original position. What was needed was something faster, more accurate, and compact enough to install on escort ships. What was needed was high-frequency direction finding. What was needed was Huff-Duff, the physics and engineering of direction finding. To appreciate the technical achievement that Huff-Duff represented, we need to understand both the physics of radio direction finding and the engineering challenges involved in making it work in the harsh environment of the North Atlantic. Radio waves are electromagnetic radiation, similar in nature to visible light, but with much longer wavelengths. The U-boats transmitted on high frequencies, generally in the range of 3 to 30 megahertz, corresponding to wavelengths of about 10 to 100 meters. These frequencies were chosen because they offered good long-range propagation characteristics. Radio waves at these frequencies could travel hundreds or even thousands of kilometers by bouncing off the ionosphere. The fundamental principle of direction finding is straightforward. A radio wave arrives at a receiving antenna from a specific direction, and if you can determine that direction, you know where the transmitter is relative to your position. The challenge lies in making this determination accurately and quickly. The earliest direction-finding systems used rotating loop antennas. A loop antenna is simply a coil of wire forming a closed loop, typically circular or square. Such an antenna has a directional pattern. It receives signals most strongly when the incoming radio wave is perpendicular to the plane of the loop, and it receives nothing when the wave arrives parallel to the loop plane. This creates a characteristic figure-8 reception pattern. By rotating the loop and monitoring signal strength, an operator could find the direction of minimum signal, the null point, which indicated the bearing to the transmitter. The null point could be determined fairly precisely because the signal drops off sharply near the minimum. However, there's an ambiguity. A loop antenna can't distinguish between a signal coming from 0 degrees or 180 degrees, since both produce the same null pattern. This 180-degree ambiguity had to be resolved using other methods, such as a supplementary sense antenna. These rotating loop systems were too slow and cumbersome for shipboard use against mobile targets like U-boats. The operator had to physically rotate the antenna, search for the null, and record the bearing. The entire process might take 3 to 5 minutes, during which time a U-boat traveling at 15 knots could move a mile or more. Moreover, the equipment was large and sensitive to ship motion, making accuracy difficult in rough seas. The breakthrough that enabled Huff-Duff came from British and French researchers working in the late 1930s and early 1940s. The key innovation was the development of cathode ray direction finding systems, which eliminated the need for mechanical rotation and dramatically improved both speed and accuracy. The cathode ray direction finder used an arrangement of fixed antennas, typically a cross pair of loop or vertical antennas oriented at right angles to each other. When a radio signal arrived, it induced voltages in both antenna elements. The relative amplitude and phase of these voltages depended on the direction from which the signal came. These antenna signals were then fed to the vertical and horizontal deflection plates of a cathode ray tube, essentially an oscilloscope or primitive television screen. The electron beam in the tube would deflect based on the antenna signals, creating a glowing trace on the screen. Crucially, the angle of this trace corresponded directly to the bearing of the incoming signal. An operator watching the screen would see the trace appear when a signal was received, instantly showing the bearing. With practice, an operator could read a bearing within a few seconds of a transmission starting. The improvement over rotating loop systems was dramatic. What had taken minutes now took seconds, and accuracy improved from perhaps plus or minus 10 degrees to plus or minus 2 degrees or better. The engineering challenges in implementing this system were substantial. First, the antennas had to be carefully designed and matched to ensure accurate bearing determination. Any asymmetry or imbalance in the antenna system would introduce bearing errors. On a steel warship, with metal structures all around creating reflections and distortions, maintaining accurate antenna patterns was difficult. Second, the receiver electronics had to be sensitive and stable. Remember, this was the era of vacuum tubes, not transistors or integrated circuits. A Huff-Duff receiver might contain dozens of tubes, each consuming power, generating heat, and requiring replacement periodically. The circuits had to maintain their calibration despite temperature changes, humidity, salt spray, and the constant vibration of a ship at sea. Third, the display system had to be reliable and easy to interpret under combat conditions. The cathode ray tube had to produce a clear, bright trace visible even in daylight. The operator had to be trained to quickly read bearings and recognize the characteristics of different types of signals. Not every radio transmission was from a U-boat, and distinguishing genuine contact from false alarms or friendly transmissions was crucial. The British took the lead in developing operational Huff-Duff systems for naval use. The key figure was Robert Watson Watt, better known for his work on radar, but whose team also contributed to direction-finding technology. By 1940, working prototypes existed, and by 1941, production systems were being installed on escorts. The standard British shipboard Huff-Duff system was designated FH3 and later improved models like FH4. These were compact enough to install on corvettes and destroyers, with the antenna mounted on the mast and the operator station located in the radio room or on the bridge. The entire system weighed a few hundred pounds and drew a few hundred watts of power. Significant resources on a small warship, but manageable. The American Navy developed parallel systems, designated DAQ and later models, with generally similar capabilities. As U.S. shipbuilding ramped up in 1942 and 1943, new escorts were increasingly fitted with Huff-Duff as standard equipment. The operational use of Huff-Duff exploited both its speed and its accuracy. When a U-boat transmitted, multiple escorts in a convoy screen could take simultaneous bearings. These bearings would be reported to the convoy commodore or senior escort commander, who could quickly plot them on a chart. Where the bearing lines crossed, there was the U-boat. This triangulation was far more accurate than any single bearing. If two ships 30 kilometers apart both took bearings accurate to plus or minus 2 degrees, their bearing lines would cross in a relatively small area, perhaps a few kilometers across. That was close enough to vector an escort to the submarine's position and force it to dive, breaking contact with the convoy. Even better, Huff-Duff could track U-boats that were shadowing a convoy without attacking. Remember, the Wolfpack tactic required the first boat to find a convoy to transmit regular position reports. Every time it transmitted, Huff-Duff operators could take bearings. Plot enough bearings, and the shadowing submarine's position and course became clear. Escorts could then be detached to hunt that submarine specifically, driving it off before the rest of the pack arrived. The system had limitations. Huff-Duff was a line-of-sight technology, the direct radio wave from transmitter to receiver. The range was limited to perhaps 25 to 50 kilometers depending on conditions, antenna height, and transmitter power. Beyond that range, the curvature of the Earth blocked the direct signal, and any bearings obtained were from skywave propagation. Signals bounced off the ionosphere, which were much less reliable for direction finding. This meant that Huff-Duff was most effective at tactical ranges, detecting and tracking U-boats in the immediate vicinity of convoys. For strategic intelligence, locating U-boats hundreds of kilometers away, the Allies relied on shore-based direction-finding networks with much larger antennas and more powerful receivers, which could detect transmissions across thousands of kilometers and triangulate positions through coordination between widely separated stations. But for convoy defense, tactical Huff-Duff was exactly what was needed. It gave escorts the ability to detect U-boats before they attacked, to locate shadowing submarines, and to vector hunters onto contacts. It transformed the battle from blind, groping in darkness to something approaching situational awareness. Deployment and tactical application. The deployment of Huff-Duff to escort vessels began slowly in 1941 and accelerated through 1942 and 1943. The Royal Navy prioritized equipping its most modern escorts first, but even older corvettes eventually received the equipment. By mid-1943, most British and Canadian escorts carried Huff-Duff, as did the rapidly expanding American escort fleet. Training operators was crucial. Reading a Huff-Duff display required skill and experience. The operator had to instantly recognize when a trace appeared, read the bearing accurately, and assess whether the signal was worth reporting. False alarms could send escorts chasing ghosts, leaving the convoy vulnerable. Missed contacts could be fatal. Operators learned to distinguish different types of transmissions by their characteristics. U-boat transmissions had distinctive patterns. They were typically short, lasting only seconds to a minute or two to minimize exposure to detection. They used specific frequencies. Experienced operators could even recognize individual submarines by subtle characteristics of their transmitters, much as a trained ear can recognize different voices. The tactical doctrine for using Huff-Duff evolved rapidly as experience accumulated. Initially, escorts would respond to Huff-Duff contacts by racing toward the bearing, hoping to catch the submarine on the surface. However, this often pulled escorts away from the convoy, creating gaps in the screen that other U-boats could exploit. German submarine commanders learned to use decoy transmissions to draw off escorts. More sophisticated tactics emerged. If Huff-Duff detected a shadowing submarine, one escort might be detached to investigate while others maintained the screen. If the contact was ahead of the convoy might alter course to avoid the area. If multiple contacts appeared, indicating a forming wolf pack, the convoy commander could request air support to arrive at dawn, when the U-boats would be most vulnerable. The integration of Huff-Duff with other systems multiplied its effectiveness. Radar was becoming increasingly important in the Battle of the Atlantic. By 1942, escorts were being fitted with cinemetric radar, operating at wavelengths of about 10 centimeters, using cavity magnetron technology that made radar sets small enough and powerful enough for effective use against submarine targets. Cinemetric radar could detect a surfaced U-boat at ranges of several kilometers, even at night or in poor weather. However, radar had its own limitations. It was less effective in rough seas, when waves created clutter on the display, and it could be foiled if the submarine ran at low speed with only the conning tower exposed, presenting a minimal radar cross-section. Huff-Duff and radar were complementary. Huff-Duff could detect a submarine at the moment it transmitted, often before it was within radar range, giving the escort a vector to search. Once the escort closed the range, radar could pick up the target and guide the final approach. Together, these electronic systems gave escorts the ability to find and engage submarines in conditions where visual detection was impossible. Depth charges remained the primary anti-submarine weapon through most of the war. These were essentially large drums filled with high explosive, typically 300 pounds of TNT or similar explosive, set to detonate at a specific depth. They were rolled off the stern of an escort or thrown to the sides using projectors called K-guns. A pattern of depth charges would be dropped around the estimated position of a submerged submarine, creating a wall of explosions that could crush the submarine's hull if close enough. The problem with depth charges was that they required the submarine to be submerged and the escort to pass directly over or very near the target. Against a surface submarine running at high speed, depth charges were useless. What was needed was a weapon that could engage a surface target before it could dive. The Hedgehog, introduced in 1942, partially addressed this need. This weapon fired a pattern of 24 small projectiles ahead of the ship in an elliptical pattern. Each projectile contained about 35 pounds of explosive and would detonate on contact with a solid object, like a submarine hull, rather than at a set depth. The Hedgehog allowed an escort to maintain sonar contact during the attack run and attack without overrunning the target. But the most effective weapon against U-boats proved to be aircraft. Long-range patrol planes, equipped with radar, depth charges, and eventually acoustic homing torpedoes, could cover vast areas of ocean and pounce on surface submarines. By 1943, the air gap, the mid-Atlantic region beyond the range of land-based aircraft, was being closed by escort carriers and very long-range aircraft like the B-24 Liberator. Huff-Duff contributed to air operations by helping to vector aircraft to submarine positions. Shore-based direction-finding networks would triangulate U-boat transmissions, providing patrol aircraft with search areas. Escort carriers could launch aircraft to investigate Huff-Duff contacts reported by the convoy escorts. The German response to the growing threat from Allied electronics was multifaceted but ultimately inadequate. U-boats were fitted with radar detectors, called METOX and later Naxos, which could warn of approaching aircraft by detecting their radar transmissions. However, these detectors were imperfect. They sometimes failed to detect radar, gave false alarms, or detected friendly radar sets. More fundamentally, the Germans never developed an effective counter to Huff-Duff. They recognized that their radio transmissions were being detected and located, but the Wolfpack tactic fundamentally required radio communication. Donitz experimented with radio silence, but this made coordinated attacks impossible and surrendered the primary advantage of the Wolfpack system. Some technical measures were attempted. U-boats were instructed to transmit as briefly as possible, using high-speed Morse or even burst transmissions that lasted only seconds. Transmission power was reduced when possible, but these measures only marginally reduced the effectiveness of Allied direction finding. The Germans also never fully appreciated how much the Allies were able to learn from their radio traffic. Not only was Enigma being broken at Bletchley Park, providing detailed intelligence on U-boat positions, plans, and operations, but the pattern of radio transmissions itself revealed tactical information. Even without reading the messages, Allied analysts could deduce when wolf packs were forming, identify which boats were operating together, and estimate operational patterns. The turning point, 1943. The period from late 1942 through mid-1943 marked the crisis and turning point of the Battle of the Atlantic. The competing factors of U-boat numbers, Allied defenses, technology, and intelligence all reached critical mass simultaneously. On one side, the German submarine force reached its peak strength. In early 1943, Donitz had over 400 U-boats in commission, with perhaps 100 or more at sea at any given time. New boats were completing at a rate of about 20 per month. Improved U-boats were entering service, including the Type 9 with longer range and heavier torpedo armament. On the other side, Allied convoy defenses were finally reaching adequate strength. The escort carrier program was producing small carriers specifically designed for convoy protection. These could accompany convoys throughout their voyage, providing continuous air cover. Destroyer escorts and frigates were being built in large numbers, providing more escorts per convoy. And nearly all these new escorts were equipped with Huff-Duff, cinemetric radar, and improved weapons. The intelligence picture was also transforming. Bletchley Park had mastered the four-rotor Enigma used by U-boats, providing near-continuous reading of German submarine communications. The shore-based Huff-Duff network could track U-boat movements across the entire Atlantic. Together, these intelligence sources allowed Allied commanders to route convoys away from known U-boat positions and to concentrate forces against wolf packs. The crisis came in March 1943. That month saw some of the largest and most intense convoy battles of the entire war. The German submarine force threw everything it had at the convoy routes. In a series of major battles, over 100 merchant ships were sunk in a single month. But the cost to the U-boats was also rising sharply. Where previously a submarine might make several patrols before being sunk or damaged, now the attrition rate was climbing toward 30% per month. Unsustainable losses that would destroy the U-boat force within a few months if they continued. The battle for Convoy ONS 5 in late April and early May 1943 exemplified the new dynamics. This slow convoy of 42 merchant ships was protected by a powerful escort group with multiple destroyers, corvettes, and a frigate, all equipped with the latest electronics, including Huff-Duff. A wolf pack of over 40 U-boats was directed against it. For several days, the submarines attempted to overwhelm the escorts through sheer numbers. They sank 13 merchant ships in fierce night battles. But the escorts, guided by Huff-Duff bearings and radar contacts, destroyed or badly damaged 7 U-boats and forced many others to break off the attack. Air support from long-range patrol aircraft sank additional submarines. The exchange ratio had fundamentally shifted. For the first time, U-boats were being destroyed faster than merchant ships. The battle demonstrated that even a large wolf pack could no longer guarantee success against a well-defended convoy with adequate escorts and good intelligence. Huff-Duff played a crucial role throughout the battle. The escorts obtained dozens of bearings on U-boat transmissions, allowing them to track the submarines attempting to shadow and attack the convoy. When U-boats tried to form ahead of the convoy for a daylight, submerged attack, Huff-Duff detected their coordination transmissions and the convoy altered course to avoid them. When submarines reported the convoy's position to headquarters, Huff-Duff bearings allowed escorts to locate and suppress the shadowers. After ONS 5, the German submarine command faced an increasingly dire situation. In May 1943, losses spiked to 41 U-boats destroyed in a single month, nearly 20% of the operational force. These losses were unsustainable. Donitz was forced to withdraw his submarines from a North Atlantic convoy routes temporarily, a de facto admission of defeat. The withdrawal wasn't permanent. U-boats would return, operating in other areas, trying new tactics, introducing new technologies. But the balance had permanently shifted. Never again would U-boats seriously threaten to sever the Atlantic supply lines. The statistics tell the story. In the second half of 1943, U-boat sinkings of merchant ships dropped by more than half compared to the first half of the year, while U-boat losses remained catastrophically high. Technical evolution and countermeasures. The success of Huff-Duff drove continuous technical evolution throughout the remainder of the war. Both sides sought to enhance their capabilities and counter enemy systems. On the Allied side, improvements to Huff-Duff focused on increased accuracy, better integration with other systems, and reduced operator workload. Later models featured automatic bearing indication, where the system would lock onto a transmission and digitally display the bearing, removing some of the subjectivity from operator interpretation. Multiple Huff-Duff sets could be linked together electronically, automatically combining bearings from different ships to produce a position fix. The shore-based direction-finding networks also evolved. By late in the war, these networks consisted of dozens of stations scattered around the Atlantic Rim, from Greenland to West Africa to the Caribbean. Advanced communications systems allowed rapid exchange of bearing data, and dedicated plotting rooms could produce near real-time tracking of all U-boat radio activity. This strategic Huff-Duff network provided convoy routing authorities with comprehensive intelligence on submarine dispositions. Frequency coverage was expanded. Early Huff-Duff sets covered only the primary U-boat communication frequencies, but later models could monitor a wider spectrum, catching transmissions on alternate frequencies or emergency channels. This defeated German attempts to evade detection by frequency hopping or using unexpected channels. On the German side, efforts to counter Huff-Duff were constrained by the fundamental requirement for radio communication. The Kriegsmarine experimented with several approaches, none ultimately successful. One approach was to develop very short burst transmissions. If a message could be compressed into a transmission lasting only a second or two, perhaps Huff-Duff operators wouldn't have time to take a bearing. Special encoding systems allowed messages to be prepared in advance, then transmitted at high speed. However, Allied Huff-Duff operators proved adept at catching even very brief transmissions, and the electronic display responded essentially instantaneously to signals. Another approach was to use relay submarines. Rather than having U-boats in the operational area transmit directly to headquarters, they would send their messages to a relay submarine stationed several hundred kilometers away, which would forward the messages. This was intended to deceive Allied direction finding about submarine positions. However, it proved operationally cumbersome, and Allied intelligence quickly recognized the relay pattern and compensated. The Germans also attempted to exploit Huff-Duff's line-of-sight limitations through tactical positioning. U-boats were instructed to transmit when far from the convoy, hopefully beyond Huff-Duff range. However, this constrained operations and didn't address the shore-based strategic direction-finding network, which could detect transmissions from anywhere in the Atlantic. More fundamentally, the Germans worked on submarine designs that wouldn't need to surface frequently. The Type XXI U-boat, introduced late in the war, represented a revolutionary design, essentially the first true submarine rather than a submersible torpedo boat. With a streamlined hull, massive battery capacity, and a snorkel device allowing diesel operation while at shallow depth, the Type XXI could remain submerged for extended periods and cruise at 17 knots underwater. Had these submarines entered service in large numbers earlier, they might have transformed the battle. Their underwater performance would have made them far harder to detect and attack. However, they arrived too late and in too small numbers to affect the war's outcome. Of about 120 Type XXI boats built, only 2 made operational patrols, neither of which engaged the enemy. The snorkel itself, introduced on older U-boats in 1944, was a partial solution to the detection problem. This was essentially a retractable pipe that allowed a submerged submarine to run its diesel engines while at periscope depth, drawing air through the snorkel and exhausting through it. This allowed battery charging without fully surfacing, reducing exposure to radar and visual detection. However, snorkel operation was slow and uncomfortable for the crew. The submarine had to remain at shallow depth where wave action was significant. If a wave washed over the snorkel head, the automatic valve would close, causing the engines to suck air from inside the submarine, creating painful pressure changes for the crew. And snorkeling submarines were still vulnerable to detection by radar, sonar, or even visual observation of the snorkel headwake. Perhaps more importantly, the snorkel didn't address the fundamental radio communication requirement. Submarines still needed to receive orders and transmit reports, which meant raising an antenna and broadcasting, exposing themselves to Huff-Duff detection. The intelligence integration, Ultra and Huff-Duff. The full power of Huff-Duff emerged when it was integrated with other intelligence sources, particularly the decrypted Enigma signals known as Ultra. This integration represented one of the war's greatest intelligence achievements and demonstrated the power of fusing multiple intelligence disciplines. The relationship between Ultra and Huff-Duff was synergistic. Ultra provided strategic intelligence, German submarine orders, planned operations, rendezvous points, patrol areas, weather reports, status reports. This high-level intelligence gave Allied commanders the big picture of U-boat operations across the entire Atlantic. However, Ultra had limitations. Decryption took time, sometimes hours, occasionally days if German operators had made mistakes that complicated the code breaking. Radio messages had to be intercepted, passed to Bletchley Park, decrypted, translated, analyzed, and disseminated. The information was often somewhat dated by the time it reached operational commanders. Moreover, ultra-intelligence had to be protected at all costs. If the Germans discovered that Enigma was compromised, they would change their procedures, potentially rendering years of code-breaking work useless. This meant that Ultra couldn't always be acted upon directly. Operational commands had to maintain plausible alternative sources for their intelligence-based decisions. Huff-Duff provided the tactical complement to Ultra's strategic intelligence. Where Ultra told you where U-boats were supposed to be yesterday, Huff-Duff told you where they were right now. Where Ultra revealed the overall plan, Huff-Duff exposed the moment-by-moment execution. The fusion of these sources created a comprehensive intelligence picture. Ultra might reveal that a wolf pack of 15 submarines was being formed to operate along.